Hello viewers and welcome to the e-learning classroom. So today we are going to look at KCSE paper 2 2022, that is KCSE 2022 paper 2, the marking scheme. So let's start with the section A. So section A has 25 marks, so we go straight to question 1. Figure 1 shows 3 cardboards A, B and C with holes placed between a source of light and an observer. So you can see the source of light and the 3 cardboards A, B and C with holes at different positions. Explain what is observed. So the eye does not see the light. That is observation. The eye does not see the light from the source since the holes are not in a straight line. This shows that light only propagates in a straight line. So in other words, they are testing the linear propagation of light. So in other words, you realize that you cannot see the light from the source because the holes are not in a straight line. Question 2. State how a polythene rod acquires negative charge when it is wrapped by a piece of cloth. State how a polythene rod acquires negative charge when it is wrapped by a piece of cloth. The cloth loses some electrons to the polythene rod upon rubbing. Hence, polythene has greater number of electrons than protons. So you realize that polythene initially, the number of protons is always equal to the number of electrons, but when you rub, it gains electrons from the cloth. That means electrons become more than proton. So we say now it is negatively charged. It's important to note that when you rub something, it can either lose electrons or gain electrons, whereby when it loses electrons, it becomes positively charged because protons become more than electrons. And when it gains electrons, it becomes negatively charged because the number of electrons become more than protons. So question 3, state one device that can be used to detect microwaves. State one device that can be used to detect microwaves. So the devices, we have crystal detectors, solid state diodes, radar, barometers, antennae, among others. Question 4. Figure 2 shows an incomplete circuit. Complete the circuit by inserting a cell so that the current high flows in the direction shown when the switch is closed. So you can see the circuit there. We have a switch, a bulb, connecting wires. So you are told to complete by inserting a cell, only one cell, so that now current flows in the direction indicated. So remember, current flows from positive terminal to negative terminal. That means on the left we'll have the longer line, and then on the right we'll have the shorter line, so that we have a cell with a positive sign on the left, negative sign on the right. Question 5. State the basic law of magnetism. So it says that like poles of magnets repel while unlike poles attract. That is the basic law of magnetism. It states that like poles of magnets repel while unlike poles attract. Remember, when you are stating a law, you just quote the ones as they appear in the book. Question 6. Figure 3 shows a vertical object O placed in front of a concave mirror whose principal focus is at F. We are told that figure 3 shows a vertical object O placed in front of a concave mirror whose principal focus is at F. You can see the diagram there. Draw a ray diagram to show how the image is formed. A ray diagram to show how the image is formed. So that means we'll have we'll just pick 2 rays to locate the image. We just require a minimum of 2 rays. So we can pick a ray parallel to the principal axis, a ray close and parallel to principal axis. So this one converges through the focal point because we are using a concave mirror. Then a ray through center of curvature, which is reflected back along the same line. So it has 2 arrows. Where the reflected rays meet, that is where the image is formed. So we have picked a ray parallel through F and then a ray through C, which has 2 arrows, and then where they meet, the reflected rays meet. That's why now the image is formed. Remember, you can also pick a ray through F, which will be reflected parallel. A ray through F parallel. You can also pick a ray through the pole, whereby you realize the angle of incidence must be equal to the angle of reflection through the pole, so you still get the meeting point as what we have there. Remember, all the rays are real, so that means we'll have complete lines. We'll not use dotted lines anywhere because of the rays are real. Question 7. State 2 properties of soft iron that makes it suitable for use as the core of the electromagnet of an electric bell. 2 properties of soft iron that makes it suitable for use as the core of the electromagnet of an electric bell. So 1, soft iron. It has high magnetic permeability. In other words, it is able to concentrate the magnetic field lines, forming a stronger field because it concentrates the magnetic field lines. Then another point is that soft iron is easily magnetized and demagnetized. Remember, the electric bell works on the principle of magnetization and demagnetization, where now the hammer is attracted. When the soft iron armature is attracted, the hammer hits on the gong. So you realize that there is magnetization and demagnetization, which takes place at a very high frequency. So we are saying now that soft iron is suitable because it can easily be magnetized and demagnetized. Also, it has a high magnetic permeability. Question 8. State 1 reason why sound travels faster at sea level than on high mountains. 8a. State 1 reason why sound travels faster at sea level than on high mountains. So you realize that at sea level the temperature is higher, therefore sound travels faster where the temperatures are higher. Another point is that at sea level air is denser. Remember, there is humidity, there is moisture in the air from evaporation. So we are saying now that air is more denser, and that means sound travels faster where the propagation medium is denser. So in other words, because air is denser in the sea level, then it means definitely sound will travel faster at sea level than on high mountains. It's very, very important to know that for this kind of a question, because you have sea level and high mountain, you should use comparative language. You must compare the two. Question 8b. State 1 condition necessary for 2 progressive waves to form a standing wave. State 1 condition necessary for 2 progressive waves to form a standing wave or a stationary wave. So 1, the waves must be in phase. The 2 waves must be in phase to form a standing wave. Number 2, the 2 waves must have equal amplitude. And then lastly, the waves should be moving in opposite directions. Remember, a standing wave is a wave whose amplitude is 0. That means the amplitudes of these 2 progressive waves must be able to cancel each other. So that now when you add, you get a 0 from the principle of superposition of waves. So we are saying now that you realize that the waves must have equal amplitude, be in phase. And remember, if they are not in phase, then they should be completely out of phase. That is 360 degrees out of phase. Then another point is that the wave should be moving in opposite directions. Let's go to question 9. 2 students stand 300 meters from a wall. One bangs 2 pieces of wood together, and at the same time, the other starts a stopwatch. They hear an echo after 1.8 seconds. Determine the speed of the sound in air. So you have the distance from the wall and time for the echo. So we know as long as you're dealing with an echo, the formula velocity is equals to d all over t, because sound propagates towards the wall and then it is reflected back for you to hear the echo. That means the distance is twice. So velocity is 2d all over t. That means 2 times 300 divided by 1.8. Then you get the value to be 333.3 meters per second. Question 10. During an experiment to investigate the relationship between the angle of incidence high and angle of refraction r for a ray of light traveling from air to glass, the values of sin high and sin r were determined. On the axis provided, sketch the graph of sin I against sin r for the values that were obtained. So we have the graph of sin I against sin r. That is to investigate the light traveling from here to glass. So in that case, you realize that the ratio is always constant. That means the two are directly proportional. So the graph is a straight line with a positive gradient and passing through the origin. A straight line with a positive gradient passing through the origin, as you can see. State how the refractive index of the glass can be obtained from the graph. How the refractive index of glass can be obtained from the graph. We know refractive index is sin I over sin r, and that means from the graph, sin I over sin r, the change in sin I over sin r is a slope. That means you just require to find the slope, and then that now becomes the refractive index. Let's go to question 11. Figure 4 shows a circuit consisting of two resistors of 4 ohm and 8 ohm. A cell had voltmeters V1 and V2. We have a cell, two resistors in series, and then you have two voltmeters. It is observed that voltmeter 2 shows a higher reading than voltmeter 1. Explain this observation. So if you look at this diagram here, you realize that current passing through the two resistors is equal because the two are in series. That means current from positive terminal passes through resistor 1, then through resistor 2, then back to the negative terminal. So that means current is common, and it is also the total current. So why do we have V2 giving a higher reading than V1? So definitely we know voltage is high R, current times resistance. But because current is equal, then we are considering now the resistance. V equals IR. So I is the same. So that means now because R2 is greater than R1, even voltage 2, V2 will be greater than V1. In other words, we can say since same current flows through the two resistors, and we know V equals high R, the greater the resistance, the greater the voltage. Question 12. A heating element is rated 3 kilowatt, 240 volt. Determine the resistance of the element. So you are given power in kilowatt, and you're also given the voltage. So we know power is V squared over R. Power is given by V squared over R. So we just replace the values. Power is 3000 kilo. Remember, kilo is the number. Kilo means 10 power 3. So 3 kilowatts means 3000 watts. So 3000 equals 240 squared all over R. Then you get the value of resistance is 19.2 ohm. Question 13. State two characteristics of images formed by diverging lens. Two characteristics of images formed by, the keyword is diverging lens. So one, the images are upright or erect. The images are upright or erect. The images are virtual. Then lastly, the images are diminished. So we have three properties there: upright, virtual, and diminished. Those are the images formed by diverging lens. So that's all about section A. 25 marks of section A. So I want us now to go to proceed now to section B, which has 55 marks. So let's start now with question 14a. State Lenz's law of electromagnetic induction. State Lenz's law of electromagnetic induction. So it states that the direction of induced EMF is such that the induced current which it causes to flow produces a magnetic effect which opposes the change producing it. It states that the direction of induced EMF is such that the induced current which it causes to flow produces a magnetic effect which opposes the change producing it. So that is our Lenz's law. To better understand it, you can consider question B. So you have a magnet. We are told figure 5 shows a magnet held near a stationary solenoid. So you can see the solenoid, galvanometer, and the magnet. That means as the magnet moves towards the solenoid, of course, current will be induced in the coils, and in that case, now the current induced in the coils will create a north pole on the right hand side of the coils, and a south pole on the left side of the coils. That means if you're moving a magnet towards the coil, it forms a north pole towards the coil on the right hand, meaning it is repelling. The north pole is repelling the magnet, which is moving towards the coil. And if it is moving away, then it forms a south pole, meaning it will be attracting the magnet, which is moving away. In other words, we are saying in Lenz's law is that the induced EMF or current produces a magnetic field that opposes the change causing it or producing it. So let's look at the first question, Roman 1. State what will be observed on the galvanometer when the Roman 1 north pole head is pushed into the solenoid. North pole into the solenoid. That means the galvanometer deflects and returns back to zero. We are only stating. So the galvanometer deflects and returns back to zero. Roman 2. Magnet is held stationarily inside the solenoid. So if it is held stationary, it means there will be no deflection of the galvanometer, meaning there will be no current flowing. Remember, for current to flow or to be induced, there must be a magnetic flux linkage or change, a change in magnetic flux linkage. That means if the magnet is not moving, or the coil, if one of them is not moving, definitely there will be no induced current. And that means now there will be no deflection. Roman 3. North pole hand is pulled out of the solenoid. So when you pull it out, this one will be opposite Roman 1. So that means now the galvanometer deflects in the opposite direction and returns back to zero. The keyword there is opposite direction, because in Roman 1 we are moving towards the coil, so it reflects and come back to zero. Roman 3, you are pulling it out. That means now it deflects in the opposite direction and returns back to zero. Question C. Explain what would be observed if the north pole of the magnet is now moved into the solenoid at a higher speed. Explain what would be observed if the north pole of the magnet is now moved into the solenoid at a higher speed. The keyword is higher speed. There is greater deflection of the galvanometer before returning back to zero, since there is greater induced current due to faster rate of magnetic flux linkage. So when you move it at a higher speed, more current will be induced because the rate of magnetic flux linkage will be faster. So that means you should be able to score the 3 marks. Then question D. State 2 causes of energy losses in a transformer. Energy losses in a transformer. The first one is hysteresis losses due to magnetization and demagnetization we have hysteresis losses. Number 2, eddy currents. Then we have copper losses due to heating effect. And lastly, flux leakage. Flux leakage. These are the 4 energy losses in a transformer. Flux leakage, copper losses due to heat, eddy currents, and the hysteresis loss, the process of magnetization and demagnetization. So with that, now I want us to go to the next question, that is question 15. Question 15. State the function of the ring's main circuit in a domestic wiring system. Function of ring's main circuit in a domestic wiring system. So it supplies electric current to the sockets. The keyword. The ring's main circuit supplies electric current to the sockets. B. Figure 6 shows a circuit consisting of switches S1, S2, and S3, and 3 identical lamps L1, L2, and L3 connected to the mains supply through a fuse. You can see the fuse, bulb 1, L1, L2, and L3. Those are 2 more bulbs. We have 3 switches S1, S2, and S3. And then we have live wire and neutral wire. Roman 1, identify 2 faults in the circuit. 2 faults in the circuit. So the first fault is that S1 should be on live wire and not on neutral wire. So that is a switch 1 should be on live wire and not on neutral wire. Then switch 3 is not necessary, or is not important. Those are the 2 faults. Roman 2, state the reasons for the answer in 15b, Roman 1, the reasons for the 2 faults. So let's start with the first one. S1 should be on live wire and not on neutral wire, since live wire is in full potential and neutral wire is at 0 potential. Live wire, we know live wire is the one that is in full potential. That means if the switch is on neutral wire, definitely the bulb will still be in live wire. That means the full potential. That's what we are saying now, that the switch should be on live and not on neutral, which is at 0 potential or 0 voltage. Then S3 is not necessary, since it is short circuits lamps L2 and L3. Switch 3 actually is not helping. It's not switching off anything there, because current will still pass through switch 2 and L2 and L3 and back to neutral. That means switch S3 is just short circuiting the 2 bulbs, so it's not important. Describe how the brightness of lamps L1, L2, and L3 compare when the switches S1 and S2 are closed. When you close S1 and S2, so you realize that lamp L1 is brighter than lamps 2 and 3. Of course, if you look at the current, the path of the current from live through the fuse, then there is a junction. One junction passing through L1, the other one passing through L2 and L3. So you realize that through L1, there will be more current, because there is less resistance on that route. But through L2 and L3, those are 2 bulbs. And remember, each bulb has an internal resistance. So realize that more current will pass through L1 compared to L2 and L3, which have more combined resistance. Then another point to note is that L2 and L3 have the same brightness. L2 and L3 have the same brightness, but we have seen that, of course, it is less than that one of L1. Explanation we have already given. Explain the answer in 15b Roman 3. We have explained, we have seen that L1 is brighter because it has less resistance compared to L2 and L3 combined. That means more current passes through L1 than in L2 and L3. That's why it is brighter. Then we have also said that L2 and L3 are sharing the same current. That's why they have equal brightness, because the same current that passes through L2 will still pass through L3 and back to neutral. That means brightness is equal for those two bulbs. Let's go to question 16. Figure 7 shows a circuit consisting of a cell in series with a galvanometer and two metal plates A and B. Figure 7 shows a circuit consisting of a cell in series with a galvanometer and two metal plates A and B. It is observed that when a beam of UV radiation falls on B, the galvanometer diffracts. Explain this observation. We have UV. A beam of UV falls on plate B. Then we are told there is deflection on the galvanometer. Explain. So the UV radiation dislodges photoelectrons from plate B, which are in turn attracted to plate A, which is connected to the positive terminal. Hence, they move to A, completing the circuit, and the current flows. So what we are saying, if you have UV radiation on plate B, remember B is connected to negative terminal of the cell, and A is connected to positive terminal of the cell. So we are saying plate A is positive. In other words, A is anode connected to positive. B is cathode connected to negative terminal of the battery or the cell. So what we are saying, when photoelectrons are dislodged from B through photoelectric effect, then they are attracted to A, which is the anode, and therefore as they flow through between B and A, they are now completing the circuit, and that is why now the galvanometer deflects. Explain what would be observed on the galvanometer when a more intense beam of UV radiation is used. The keyword there is more intense beam of UV radiation is used. So the galvanometer deflects more since the photoelectrons are dislodged from plate B, which are in turn attracted by plate A, completing the circuit, and more current flows. So we have said that the galvanometer deflects more. The galvanometer deflects more, and the reason for that is that, if you use a more intense beam of light, beam of UV, then it means even more photoelectrons will also be dislodged, and the more the photoelectrons, of course, now the more they will be attracted, now completing the circuit, causing more current to flow. B Roman 1. State with a reason how the intensity of an X-ray beam can be increased in the X-ray tube. How the intensity of an X-ray beam can be increased in an X-ray tube. By increasing the heater current, which in turn dislodges more electrons through the muonic emission. Hence, on striking the metal target, more X-rays are produced. So we are saying if you want to increase the intensity of X-ray beam, then definitely you increase the heater current, the keyword heater current. And we have said when you increase the heater current, then the cathode will be heated more and dislodge more electrons. And when more electrons are heated, of course, they will be striking the metal target, and then more X-rays are produced. Remember that question, sometimes they may also ask you how to increase the energy of the produced X-rays energy. In other words, how can you make X-rays to have a higher penetrating power? In other words, or how can you produce hard X-rays? That means you need to increase the accelerating voltage. When you increase the accelerating voltage, definitely you will increase the energy of X-rays, because kinetic energy of the X-ray have MeV squared. That's mass times velocity squared. Mass of the electrons times velocity squared. I have MeV squared is the kinetic energy. And when the electrons, beam of electrons strike the metal target, then the kinetic energy is converted to X-rays. So we are saying if you want to increase the energy of X-rays, you use a higher accelerating potential. But if you want to increase the intensity, you increase the potential of you increase the heating current. So now at least you can produce more electrons, which when they strike the metal target, now they will produce more X-rays. Roman 3, figure 8 shows the trace of an AC signal on the screen of a cathode ray oscilloscope, CRO. Figure 8 shows the trace of an AC signal on the screen of a cathode ray oscilloscope, CRO. You can see the trace of the signal on the screen of CRO as shown on figure 8. Given that the time-based setting is 8.5 milliseconds per centimeter, determine the Roman 1, the wavelength of the AC signal. The wavelength of the AC signal. So we know wavelength is given by the number of squares on the horizontal for one wave. One wave is having 2 squares on the horizontal. That means the wavelength is, each square is 1 centimeter, as you can see from the scale. That means 2 squares for one wave on the horizontal. That means the 2 squares will give you 2 centimeters as a wavelength, 2 centimeters or 0.02 meters. Roman 2, the frequency of the AC signal. Remember, frequency is given through the time-base setting, because time-base controls the X-plates. That means the horizontal now. So if you look at the one wave it has 2 squares on the horizontal, and time-base, which is now the controlling X-plates, which are now affecting the horizontal diffraction, is set at 8.5 milliseconds. That means frequency is 1 over period, and the period will be given by 2 squares. These are the horizontal number of squares forming one wave. 2 squares times time for 1 square, which is 8.5 milliseconds. Because we are told per centimeter is 8.5 milliseconds. So 8.5 times 10 raised to negative 3 milli. Remember, milli is a number, 10 raised to negative 3. So 8.5 times 10 raised to negative 3 times 2 squares, which gives you 0.017 second. Then frequency is 1 over t, 1 over period. That is 1 over 0.017, which gives 58.82 hertz. State the function of the following parts of a cathode ray oscilloscope. Roman 1, the grid. Function of the grid on CRO. So it controls the number of electrons reaching the screen by being more negative or less negative, hence the brightness of the spot on the screen. So we are saying the function of grid controls the brightness of the spot on the screen by controlling the number of electrons that are reaching the screen. So then we have Roman 2, the filament. It's the cathode to dislodge electrons through the muonic emission. Of course, we all know that the heating filament. It heats the cathode, therefore dislodging electrons through the muonic emission. Question 17. A. State one hazard of radioactivity. One hazard of radioactivity causes the skin burns, cancer, leukemia, causes cell or gene mutations. We also have hereditary effects among others. Skin burns, cancer, leukemia, we have cell or gene mutation, hereditary effects among others. Those are the dangers of radioactivity. Remember, when you're talking of radioactivity, you are referring to alpha, beta, and gamma radiations. Alpha, beta, and gamma, but the most dangerous is the gamma radiation. That means now majorly these are the same effects of gamma radiation exposure to human beings. Let's go to B. Figure 9 shows a decay curve of a radioactive element. You can see the decay curve here. We have the counts and we have the time. Counts against time. from the graph determine the half-life of the element. So you realize we are starting from 100 counts. That means half-life is the time taken for half of the counts to reduce. So from 100 to 50, 100 to 50, that means you count 5 squares, then you go horizontally and read the time. So 100 to 50, so you read 50, what is the time for 50? And then you realize it is 4.6 seconds. 4.6 seconds, that is the half-life. Just read like that. Roman 2, the number of half-lives it will have undergone when the count is 12.5. 12.5 counts. Remember, it is starting from 100, and we know each half-life, the counts will reduce by half. That means from 100 to 50, one half-life, 50 to 25, another half-life, 25 to 12.5, another half-life. So there are 3 half-lives. See Roman 1. State the effect of doping on a semiconductor. Effect of doping on a semiconductor. So doping improves the electrical conductivity of the semiconductor. It improves the electrical conductivity of the semiconductor. Roman 2. Explain how doping produces an N-type semiconductor from a pure semiconductor. How to produce any type semiconductor. So doping an intrinsic semiconductor with group 5 elements, e.g. phosphorus, will have 4 electrons bonding with the intrinsic semiconductor, e.g. silicon, since they are in group 4, and the 5th electron is donated for electrical conductivity. So that means, remember, semiconductors are mostly in group 4. We have silicon and germanium. So when you, for example, when you dope silicon, which is in group 4, with a group 5 element, for example, phosphorus. You know, phosphorus has 5 in the outermost, 5 electrons in the outermost. Silicon requires only 4 to attain stability. That means silicon will bond 4 electrons to attain stability, and then 1 electron from phosphorus will be left unbonded, and that is what is used now to conduct the electricity. In other words, N-type means the charge carriers are the negatively charged electrons. These are the electrons which are unbonded, and we have seen they come from when you dope group 4 with group 5, meaning 1 electron will be unbonded, and these are the ones that will be used now for electrical conductivity. Let's go to Roman 3. Figure 10 shows a circuit. Figure 10 shows a circuit consisting of 2 galvanometers, G1 and G2, 2 switches, S1 and S2, a cell, and 2 diodes, D1 and D2. So you can see the circuit diagram. We have a cell there, G1 and G2 galvanometers. Then we have 2 diodes, D1 and D2, and 2 switches there. Explain what is observed when switch 1 and switch 2 are closed. Switch 1 and switch 2 closed. What do you see? So both G1 and G2 deflects, but G2 has a higher deflection. Both the galvanometers, G1 and G2, are deflecting, but galvanometer 2 has a higher deflection. G1 conducts some current, but G2 conducts the total current. D1 is forward biased but D2 is reverse biased. Hence, some current passes through D1, but no current passes through D2. So if you look at the circuit, the path of the current from positive terminal to the negative terminal, so you realize that current starts from positive terminal. There is a junction for galvanometer 1 and the diode 1. That means some current will pass through galvanometer, some current will pass through diode. Then once it passes switch 1, there's another junction there, but you realize now that there is no current that can pass through switch 2 to diode 2, because diode 2 is reverse biased. That means the whole current passes through the upper junction, which combines with that one for galvanometer 1, So from diode 1, the whole current combines with that of galvanometer 1, which now passes through galvanometer 2 and back to negative terminal. That means no current passes through diode 2. So you realize through galvanometer 2, full current passes through there. Because the current passing through galvanometer 2 is both the current that had passed through galvanometer 1 and the one that had passed through diode 1. And then you realize it is combining and coming back to the negative terminal. You realize now that that's what we are saying now, galvanometer 2 is giving a higher reading than galvanometer 1. So we go to question 18a. Question 18a. Explain the effect on resistance of a diode when the forward bias voltage is increased. The effect on resistance of a diode when forward bias, the keyword is a forward bias voltage is increased. So when you increase the forward bias, you realize that the resistance normally decreases because the size of the depletion layer reduces. So the resistance decreases since the size of depletion layer reduces, hence allowing more current to pass through the diode. So that means now depletion layer, once it reduces, more current passes through the diode because now the depletion layer has been reduced. Let's look at question B. Figure 11 shows a circuit consisting of a 12 volts battery. You can see that. 1.5 kilo ohm resistor. You can see the 1.5 kilo ohm resistor. A light dependent resistor LDL. You can see LDL there. And a lamp of negligible resistance. You can see all that. The circuit can be used as a light detector. So you can see the whole circuit. We are saying that circuit is being used as a light detector. Explain what would be observed if the lighting conditions are changed from total darkness to bright light. Total darkness to bright light. There's a keyword. So it means in total darkness, the lamp does not light, but when the bright light falls on the LDR, its resistance reduces. Hence, the current flows, causing the lamp to light. In total darkness, the lamp is off because the resistance of LDR is very high. But when bright light strikes the LDR, then it lowers its resistance. And that's why now the current is able to flow and the bulb or the lamp lights. Let's go to Roman 2. If the resistance of the LDR in bright light is 1 times 10 power 3 ohm, if the resistance of the LDR in bright light is 1 times 10 raised to power 3 ohm, determine the potential difference across the 1.5 kilo ohm resistor. So looking at the circuit diagram, you're given the resistance of LDR 1.5 kilo ohm, 1 times 10 raised to power 3, that's 1000 ohm. Then you are trying to determine the potential difference across the 1.5 kilo ohm resistor. So if you want potential difference, V equals high R. So you must know which current is passing through 1.5 kilo ohm resistor. But you realize because the two are in series, the three are in series, both the lamp, LDL, and 1.5 kilo ohm. Because the three are in series, then it means total current will pass from positive terminal to 1.5 kilo ohm to LDL to lamp and back to negative. That means the current passing through 1.5 kilo ohm is the total current. And because we are looking for voltage of 1.5 kilo ohm, then it means voltage will be high R, where I is the total current, then times the resistance which we have 1.5 kilo ohm. So we first get the total current. So total current is given by V all over R, where V is a total voltage divided by total resistance. We know total resistance is 2500 ohm. That means total current will be 12 volts divided by 2500 ohm, which gives you 0.0048 ampere. Once we have the total current, which we have seen is the same current that passes through 1.5 kilo ohm and through LDR and through the lamp. So once we have the total current, then V is IR, voltage is current times resistance, so it will be 0.0048 ampere times 1500. That is from 1.5 kilo ohm, 1500 ohm. So when you multiply, you get the voltage is 7.2 volts. C. State the function of a capacitor in rectification of an alternating voltage. Function of a capacitor in rectification of an alternating voltage. So we know the capacitor smoothens the output signal. That's the function of a capacitor in AC voltage. It smoothens the output signal. D. Figure 12 shows two capacitors of 2.5 microfarad and 10 microfarad. Figure 12 shows two capacitors of 2.5 microfarad and 10 microfarad in series with a 12-volt battery. You can see that 12 volts, 10 microfarad, 12 volts, 10 microfarad and 2.5 microfarad. Determine the total charge stored by the capacitors. Total charge. So we know total charge Q equals CV, whereby C is the total capacitance, and then V, voltage, is also total voltage. So Q is CV, but now everywhere total charge, total capacitance times total voltage. So we start by getting the total capacitance. So for capacitors in series, total is given by product of a sum. That means 2.5 times 10 divided by 2.5 plus 10. Product of a sum, which gives you 2 microfarad. Then total charge. Total charge is given by CV, which is the total capacitance times total voltage. That means total capacitance is 2 times 10 raised to negative 6. Remember, micro is a number. You must work out the numbers well. Micro is a number, 10 power negative 6. So 2 times 10 raised to negative 6 times total voltage. There's a voltage across the battery, which is 12 volt. So when you multiply, you get 2.4 times 10 raised to power negative 5 coulomb. That is now the total charge. Total charge, you realize it is 2.4 times 10 raised to power negative 5 coulomb. So that is what was supposed to be written in physics paper 2. That is what was supposed to be written in a physics paper 2 in KCSE 2022 exam. So you realize it was quite a simple exam. You can also look at the topics that were tested and how many marks the topics were able to carry. So that means that's all. You may send questions and feedback through the comments section.